Hi everyone. In this video, what we're going to start talking about is atoms and atomic theory. So to start out with, what I wanted to do is just talk about Dalton's atomic theory. Dalton was not the first person to think about what matter is made out of. Turns out he was just one of the first who actually published it, and his work was actually published in the early 1800s. So for hundreds of years earlier, people thought about what the world is, what the matter is made up of. Dalton's theory, what he proposed at the time, is not 100% correct, but basically he had a couple of different postulates, parts of his theory. The first one is that all matter is composed of atoms. And now he defined an atom as being a tiny, indivisible particle of matter. Now, was he correct about that? We do think about all matter as being composed of atoms. However, this indivisible thing, we're going to come back to. Okay, so all matter is composed of atoms. And what he also said is atoms of the same element are identical. Now, this one also turns out to have a little bit of a problem. They don't necessarily have to be identical. They are alike, but they're not necessarily identical. And again, we're going to come back to that in 1 second. He said atoms of different elements are different. He actually thought that was going to be different in mass. However, they differ in a different way in addition to differing in mass. And he also said that atoms cannot be created or destroyed during chemical reactions. And his fifth and last thing is that atoms combine in small whole number ratios to form compounds. It makes sense that they have to be whole number ratios because they're indivisible in his theory. So you can never have 1.5 atoms or 1.72 atoms. You have 1 atom, or you have 2 atoms, or you have 3 atoms. Now, what did he use as evidence for his theory? The first piece of evidence he used was the law of conservation of mass. Remember, the law of conservation of mass says that mass cannot be created or destroyed by ordinary means. So if whatever materials we started with, let's say starting materials, mass has to equal the final materials mass. And he said if an atom can't be created or destroyed, that this would be why the law of conservation of mass was true. So if you started out having 100 carbon atoms and 20 oxygen atoms, you could recombine how they were connected, but when at the end, you still have to have 100 carbon atoms and 20 oxygen atoms. And so the atoms themselves don't change their identities. The atoms can just recombine in how they join up. So atoms can't be created or destroyed, meaning if you start with a carbon atom, you're going to end up with a carbon atom. Now, is this really true? This is true for non-nuclear reactions, which we don't really talk about nuclear reactions in this course, but as you go through the different chemistry classes, you can actually change one element into another element by doing a nuclear reaction. But for us in this class, whatever the atom is going to stay at. So the law of conservation of mass, if you started with 100 grams, you got to end up with 100 grams. That's got to be true. If you start with 100 carbon atoms, they have a set mass. If you have to end with 100 carbon atoms, your mass is going to be the same. So that was one piece of evidence he used. The second piece of evidence is a little more confusing to write out. He used what's called the law of multiple proportions. Now, the law of multiple proportions is long. So I'm going to write it down and then read it to you. So it says, when two elements combine to form more than one compound. The ratio of the masses of one element when compared to a given amount or same mass of a second element will always be whole numbers. That's a mouthful, right, to say. So let me show you what I'm talking about. These are two compounds most people know about. There is carbon monoxide and there is carbon dioxide. These are two compounds that are formed between carbon and oxygen. So what he's saying is if you compared these and we looked at a sample of carbon monoxide that had 12 grams of carbon in it and compared it to a sample of carbon dioxide that also had 12 grams of it. So this is my given amount, the same amount of carbon. And then if I were to look at my amount of oxygen, what I would find is I would have 16 grams of oxygen in carbon monoxide, but I'd have 32 grams of oxygen in carbon dioxide. So now if I look at these two that are different, and I do 32 divided by 16, I always get a whole number. He used this to say that atoms are indivisible, that they were the building blocks, because when you get a whole number, it means you always have a whole atom. There's never partial atoms in formulas. So his evidence is a little bit, the law of multiple proportions is a little confusing. It doesn't mean, this is not in mixtures having varying compositions. That's the number one thing people confuse this with. This is saying when you're comparing two different compounds made from the same elements, when you compare the second element's amount, when the first elements are the same mass, that this will always give you a whole number ratio. So let's talk some other nitty-gritty about atoms. Let's actually get to atomic structure. If you're reading through a textbook, they're going to go through the history of who discovered what when. I'm not really going to ask you about that. If you're curious and you want to look into it, that's great. But I'm not going to really require that for this course. So to start out with, we're going to use the modern view of an atom. And in the modern view of the atom, there are two main parts of an atom. There's the nucleus and there is the electron cloud. Nucleus means center of. The electron cloud is going to surround the nucleus. The nucleus is going to contain two types of subatomic particles. They're going to contain protons and neutrons. And cleverly enough, in the electron cloud, it's going to contain electrons. Now, some things about the nucleus and the electron cloud, when you're looking at an atom, we can think about an atom as being kind of spherical overall as a three-dimensional shape. And if you were to look at it, what you would find is the nucleus is a tiny little dot. And I can't even draw the electron cloud big enough. If this tiny dot was drawn and then you took the rest, the surroundings all around it, I don't know, maybe the size of a football field on each side. Obviously, I can't draw something that big. And you were to spin that in 3 dimensions to make it the rest, that's how much is the nucleus compared to the electron cloud. The nucleus is tiny. Tiny portion of overall volume of the atom. What I'm really saying is the atom is almost all electron cloud. The electron cloud takes up almost virtually all of it. That is true, however, most of the mass is in the nucleus. And only a tiny portion of the mass is in the electron cloud. So what does this mean in terms of density? The nucleus is very dense. The electron cloud has very low density. The nucleus is so dense that this doesn't exist, but say you were to take a whole bunch of just nuclei and smush them together till they were the size of a small pea. If you had all this being nucleus, it would have a mass of several million tons. It would be an extremely massive thing. It doesn't exist. There's nothing that I know that is as dense as a nucleus. Even black holes are not as dense as the nucleus. So what I'm telling you is that most of the atom is this electron cloud, and this electron cloud has very little mass in it, has very low density. And so what's really true is most of the atom is empty space. And so a question would then arise, if most of an atom is empty space, how do we exist? How do solid things exist? How come it's just not all space? So I'm going to give you I'm not a good artist, so just bear with this, but say I had a fan, here's my motor, and this is a very dangerous fan. All it has is 3 metal blades. Right here's the stand holding it. If the fan is off, and I asked you, can you poke your finger through the fan when it's turned off? The answer is yes, you can. You could poke your finger through in almost all of these areas, right? Any of the areas where the blades are not. The blades are these guys here, right? These are the 3 blades. Chances are you're not going to hit a blade, you're going to hit empty space. The fan is mostly empty space. However, if I were to turn that fan on high, could you put your finger through it? If these blades are rotating super fast, could you put your finger through it? The answer would be no, because the blades, as the blades are moving quickly, they seem to be everywhere all the time. They actually kind of seem like they're solid. Well, that's how an atom is also. Even though the electron cloud is mostly empty space, even though it's mostly empty space, the electrons are moving so fast. They seem to be everywhere all the time. Making the atom actually seem like it's solid, even though it's mostly empty space. So an overall view of an atom right now is that we have nucleus in the center and we have this electron cloud around it, right? And so a nucleus is going to contain protons and neutrons, and the electron cloud is going to contain electrons. So let's just take 1 minute and talk about these things. These are called subatomic particles. And the 3 subatomic particles you need to know about are electrons, protons, and neutrons. And so there's a symbol for each. Electrons is E minus, protons is P plus, neutron is N with a naught or a degree sign. And then if we were to look at their charge, what we'd find is that electrons are negatively charged. They have a charge of minus 1.6 times 10 to the minus 19 coulombs. And protons have a positive charge that happens to be positive 1.6 times 10 to the minus 19 coulombs. And neutrons are neutral. They have no charge. People don't really like using this number of coulombs. So what we typically use is what's called a relative charge. And in a relative charge, the electron is as negative as the proton is positive. So we typically say an electron has a charge of -1 and a proton has a charge of +1. That's not really their charge, that is their relative charge. And so also, if we were to look at mass of each, and this is in grams, An electron has a mass of 9.107 times 10 to the minus 28 grams. A proton has a mass of 1.672 times 10 to the minus 24, and a neutron is 1.67 times 10 to the minus 24. So if we were to round, this number, we could say 9 times 10 to the minus 28 is approximately 1 times 10 to the minus 27. Why am I saying that? Because these are 1 and this is 1. And so now I could just look at these exponents, and the difference between 10 to the minus 27 and 10 to the minus 24 is 10 to the minus 3, which is 1,000. So very roughly speaking, an electron has about 1,000th of the mass of a proton or a neutron. And what's also true is if you look at the mass of protons and neutrons, they're very close to each other. So what we typically do is we don't use their actual mass. What we're going to use is the relative mass. And when we use the relative mass, we use these units called atomic mass units, which is usually abbreviated as an AMU. And so relatively speaking, we're going to say a proton is 1 and a neutron is 1 because they're about the same. But an electron is much less, and it comes out to be somewhere around 1 over 1,828 AMUs. In decimal point, that's 0.00055-ish. It's very tiny. So what's going to be true is when we're finding the mass of an atom, lots of times we're going to ignore the electrons because they're just so much smaller in mass, on the order of magnitude 1,000 times less massive. Now remember, electrons are in the electron cloud, and both protons and neutrons are in the nucleus. Sometimes things that are in the nucleus are called nucleons, protons and neutrons, since those are found in the nucleus. So I'm going to stop this video here, and when we pick up next time, we're going to use a bunch of different terms to describe atoms, and within those terms, we're going to use these subatomic particles of electrons, protons, and neutrons.